Let's first start with clarifying the similarities and differences between categorizing gases as either conventional or unconventional. Conventional and unconventional gases do not differ as far as their chemical composition, but rather in their technological processes used in their extraction. In conventional gases, vertical drilling wells are set up wherein only a few wells are drilled. The reservoirs contain a pressure difference that allows for simple, unimpeded flow to the surface. These characteristics of conventional gases allow for low production costs and high well efficiencies. Unconventional gases, on the other hand, do not flow naturally through their enveloping sediments and therefore require more complicated techniques in order to extract them. The result is an increase in production costs and a decrease in well efficiencies, with an average unconventional well losing up to about 44% of their production in the first year. Three main gases make up the bulk of the unconventional gases, and they are shale gas, tight gas, and coal bed methane, and they are termed based on the reservoir rock they are contained in. Shale gas is trapped within the sedimentary deposition of mud, silt, clay, and organic matter. The gas is either absorbed within the organic matter or is contained within the pores of the rock. Tight gas is gas that has migrated into the low porosity and permeable reservoirs such as sandstone, siltstones, and carbonates. The pores within the rock are either irregularly distributed or badly connected through narrow capillaries due to cementation and recrystallization over time. Coalbed methane is formed during coalification, where large quantities of methane-rich gas is generated and trapped within the seams of the large internal surface area of coal. These three gases share similarities in the techniques that coincide with their extraction. First, 3D seismic imaging identifies attainable reservoirs, and it does so by utilizing an energy source that produces acoustical reflections that map out the structure and properties of subsurface rocks. Once sufficient reservoirs are found, wells are drilled horizontally to increase surface area, and the rock is then fractured by injecting a mixture of water, sand, and certain chemicals at high pressures, which then opens the reservoir and in turn allows for gases to flow into the wellbore and to the surface. Advances in both scientific theory and instrumentation have opened the door for unconventional gas production, resulting in an increase in its attention, research, and applicable developments. As a result, in 2000, shale and tight gas production made up only 1.6% of total natural gas production, whereas in 2010, shale and tight gas production made up a total of 23.1% of natural gas production. Due to these breakthroughs, today we now have 117 trillion cubic feet of unconventional gas resources that are now recoverable. Coal, petroleum, natural gas, and other mine fuels provide around 75% of U.S. electricity and 93% of other energy needs. With such a large dependence, increasing the production efficiencies of unconventional wells while preserving capital costs and asset revenues become prevalent in our increasing dependence on unconventional resources. In order to realize the full potential of unconventional resources, the industry must work to improve the variety of technical, economic, environmental, regulatory, and societal challenges that encompass all the inefficiencies surrounding production.
Shale gas is the first type of gas that we will discuss. Shale gas is created in shale formations in the ground that formed somewhere between 65 and 570 million years ago. Shale gas, like all other types of natural gas, is comprised of about 90% methane and is combined with other gases such as carbon dioxide, nitrogen, and hydrogen. It is also the most prominent type of unconventional gas, with the United States producing around 7 trillion cubic feet of the gas per year, and is still estimated to have 150 trillion cubic feet still left in the ground. Extracting shale gas uses the process of hydraulic fracturing. The apparatus consists of drilling using a high-pressure stream of water, sand, acid, and other various substances such as pH-adjusting agents and lubricants. This high-pressure mixture causes cracks or fractures to form in the shale formations. Then, the sand in the hydraulic water holds these cracks open, causing them to enlarge and allowing the gas to escape back up through the well to the surface where it is recovered. In addition to this gas being recovered, approximately 70% of the fluid or flowback is recovered as well. Producing shale gas that is economically viable is important and is achieved mainly by parameters of the drilling process itself. Some of these include the location of drill sites, the depth of drilling, and techniques and procedures used in the drilling process. One of the most essential techniques used is called horizontal drilling. This is where the well is turned 90 degrees so that it runs along the shale formation instead of passing through it. This technique increases productivity per well greatly, as one horizontal well can replace 3 to 4 vertical wells. Even with practices such as horizontal drilling, not all shale gas is economically obtainable, meaning that it costs more money to produce the gas than would be made by selling it. This is usually due to the location of the shale formations, but this can be very situational. Beyond this, there are still gas-bearing shale formations that have yet to be discovered. Together, the estimates of shale gas still remaining dwarfs the amount we have recovered so far, but technological advancements are required in order to recover it.
The second type of unconventional gas production is through tight gas reservoirs. As the need for alternative gas production increases, the use of tight gas reservoirs also expands. Tight gas reservoirs are reservoirs with low porosity and permeability. There's no global specifications for classifying tight gas reservoirs, so for the purpose of this paper, low porosity is considered to be a void less than 10%, while low permeability is less than 0.1 millidarcy. Other parameters such as in-situ stress and high water saturation can also be used to differentiate tight gas reservoirs from conventional ones. Because there is not enough natural production, hydraulic fracturing and horizontal drilling are used to extract the gas, much like in shale gas drilling. Before drilling, it is important to evaluate tight gas reservoirs in order to assess the amount of resource, the quality of the reservoir, factors controlling tight gas accumulation, and gas production. All of these considerations are necessary to increase quality, quantity, and efficiency of drilling. Two techniques used for tight gas reservoir evaluation are microcomputerized tomography and static resistant models. Micro-CT generates a 3D image of rock morphology which can then be used in numerical evaluations to calculate permeativity, porosity, and permeability. These properties can be used to understand the makeup and quality of the reservoir, which are important when setting up drilling apparatus. Static resistant models are also utilized to evaluate the contact and accumulation of hydrocarbons in the tight gas reservoir, which allows for ultimate recovery of gas. The purpose of these models and simulations are to evaluate the tight oil displacement, which can then be used to identify sweet spots in the reservoir for increased oil production. The same method of hydraulic fracturing and horizontal drilling used in shale gas recovery is used in tight gas reservoirs. Due to the low porosity and permeability of tight gas reservoirs, it is important to form complex networks of fractures so as to increase reservoir volume and contact area, thus increasing oil migration. Complex networks will not always form when fracturing, but the likelihood increases with high brittleness factor. A brittleness factor can be calculated by analyzing petrophysical properties like porosity and permeability, and this is why evaluating tight gas reservoirs prior to drilling is extremely helpful.
Alright, ladies and gentlemen, now we come to coal bed methane, which is an unconventional type of energy, similar to the previous two, which utilizes natural gas extracted from coal beds. It's becoming very revolutionary in countries that are developed, like the United States, Canada, and Australia. It's called sweet gas because it contains little hydrogen sulfide and a lack of heavier hydrocarbons like propane or butane. Instead, it contains mainly methane and trace quantities of other gases. Although the exact composition of the reservoir, as well as other characteristics like porosity, absorption capacity, fracture permeability, and etc., determine how much of the gas can be recovered, it is a growing method of extraction and energy in today's world. Alright, moving on. Here we have a beautiful illustration of a coal bed methane plant. The extraction of coal bed methane is a relatively cheap process compared to other types, such as like drilling and fracking. A steel tube is drilled into the hole seam to provide an access route to the reservoir. Natural production and or the pumping of water reduces the pressure in the coal seam, and this forces the gas and the produced water to the surface. The amount of gas that can be recovered from coal bed methane is dependent on a couple of factors. First is the porosity of the reservoir, which is a measure of how spacious it is. Another factor is fracture permeability, which is defined as how permeable the channel is for the gas to flow. A higher permeability corresponds to higher gas production. Because of coal's stress-sensitive permeability, this fluctuates depending on the applied stress. Other minor factors of impact include coal density, initial gas phase concentration, and critical gas saturation. There are pros and cons to coal bed methane. First, it is readily available and much easier to detect, and has large reserves in the developed nations like Australia, Canada, and the United States. Interesting fact, there are over 33 trillion cubic feet of reserves yet to be extracted in Australia alone. Another pro is that it is relatively cheap compared to other methods of drilling. While coal bed methane extraction has its benefits, there are also environmental concerns to consider. There's the issue of methane production. Burning coal bed methane releases a large amount of carbon dioxide, a greenhouse gas. The second issue is the production of large amounts of water containing concentrated salts, heavy metal, and chemicals. Disposal of this water without significant detriment to the surroundings is an issue that the world faces. Some methods of disposal is where the water is re-injected into isolated formations. It is often used for irrigation, frozen for reuse, or, in the worst case scenario, dumped into the surrounding area.
Although unconventional gas production expands in the amount of gas and oil available for use, there are major environmental drawbacks. The two main concerns are increased greenhouse gas production and water pollution. All three methods explained produce considerable quantities of methane and carbon dioxide which contribute to global warming. Flowback of hydraulic water, which contains chemicals and heavy metals, is another issue, seeing that it seeps to the surface in surrounding areas. These environmental drawbacks must be weighed when considering unconventional methods for gas production.